AI is moving at lightning speed. I mean, constantly breaking new ground, almost daily, it feels like. But what if the biggest bottleneck in all this AI research isn't, compute power or data, but us? Human researchers. Sounds a bit weird, right? We're the ones building it after all. Okay, let's unpack this a bit. Imagine a future where AI isn't just solving problems you throw at it, but actually inventing itself. A future where the whole process of scientific discovery in AI can speed up way beyond human limits. That's exactly what we're diving into today. We're looking at this really groundbreaking paper. It's titled SII-ARCH, AlphaGo Moment for Model Architecture Discovery, and the system behind it, called ASI-ARCH. Our mission really is to give you a clear shortcut to understanding how AI is now designing AI, how it's moving past human intuition, past that linear progress, and what that actually means for discovery itself.
Yeah, and what's really fascinating here is how this work tackles a fundamental paradox that's been brewing in the AI field. You see AI capabilities just exploding exponentially, right? Think large language models, image generation, all of it. Yet our human capacity to research this stuff, to develop new AI models, to dream up novel architectures and test them out, well, that's still pretty much linear,
Yeah.
slow and steady. And this paper, it offers a novel, really comprehensive solution that's designed specifically to shatter that very constraint.
That really is the core issue, isn't it? We're building these incredible, super fast AI brains, systems that process info at speeds we can barely imagine. But the human experts actually designing those brains, they're still operating at, comparatively slow human speed. The paper nails this, AI systems, improving exponentially. The pace of AI research, linearly bounded by us, by human cognitive capacity. This creates what they call an increasingly severe development bottleneck. It really is like having a Formula One team where the pit crew still changes tires with a hand wrench. It just doesn't scale.
Exactly. And just think about the sheer effort involved. Designing just one state-of-the-art neural architecture, that often takes months, months of hard work from dedicated human expert teams. The paper even puts a number on it, human-only research. 2,000 hours per model. That's a huge investment for just one model.
Yeah.
And it's fundamentally unscalable when you think about the need for constant innovation. You just hit the human ceiling really, really quickly.
And those older methods, the ones trying to automate bits of this, like
Yeah.
neural architecture search, NAS, they tried to help, but they had their own limits too, right?
Oh, absolutely. Traditional NAS methods were definitely powerful in their own way, but they mostly operated like a very sophisticated chef picking the best ingredients from a pantry someone else stocked. The pantry being, human invented components. They were great at optimizing within these predefined boxes that humans set up. They could find the best mix of existing building blocks, sure, but they weren't really inventing entirely new blocks or even the rules for making them. And that brings up the big question. How do you speed up the actual discovery part of AI science beyond just tweaking what you already have?
Okay, here's where it gets really interesting for me. Instead of humans painstakingly designing every single new AI model, what if AI could just design itself? What if it could not only optimize, but actually hypothesize and create fundamentally new architectural ideas? That's the really bold, ambitious vision behind ASI-ARCH. ASI-ARCH, it stands for Artificial Superintelligence for AI Research, ASI-4AI for short, and they introduce it as the first fully autonomous system built specifically for discovering neural architectures. This feels like a genuine paradigm shift, moving from just automated optimization to, well, automated innovation.
It really is about getting beyond those human-defined search spaces entirely. ASI-ARCH doesn't just pick the best option from a list. It autonomously dreams up entirely new architectural concepts. Then it implements them as actual working code, and then it rigorously tests how well they perform through real experiments. It's a complete end-to-end approach to scientific research. It basically mirrors the whole cycle of human scientific discovery, but running at machine speed.
So how does the incredible system actually work? The paper describes it as a closed-loop system for autonomous architecture discovery. Sounds almost like natural evolution, like a self-improving cycle. Driven by four main parts, these interconnected modules. Can you walk us through those?
Absolutely. So the first module is the researcher. You can think of it as the creative engine or maybe the hypothesizer. Its job is to propose new architectures. It does this based on a deep understanding of what's worked before looking specifically at the top 50 candidates it's previously explored. And crucially, it also draws on human expertise stored in its cognition base, which we'll get to. Now, this isn't just random generation. The researcher designs both the why, the architectural motivation, and the actual runnable code needed to integrate the design. It even has these built-in novelty and sanity checks to avoid wasting time in compute. So it checks if an idea is genuinely new, avoiding duplicates, and also if it's fundamentally flawed, like it prevents designs with ON2 complexity, things that would just bog down completely as inputs get bigger. Practical stuff. It also checks for things like incorrect causal masking, making sure the model doesn't accidentally cheat by seeing future data.
Okay, so the researcher sparks an idea, maps it out,
Yeah.
and that design isn't just theoretical, it goes straight to the next module, the engineer, for a real-world test drive, the experimenter, basically.
Precisely.
Yeah.
The engineer module handles all the empirical testing, running the code in a real environment. And here's something really cool, something that really sets it apart. It has this robust self-revision mechanism. So unlike older systems that might just toss out a buggy design or flag it for a human to fix, the engineer actually analyzes its own error logs, and then it fixes its own coding mistakes. It's this iterative debugging loop that's incredibly efficient. It means promising ideas don't get ditched just because of a simple typo or coding bug. It also has automated quality assurance built in, so it can terminate runs that are clearly inefficient or hopelessly buggy, saving valuable compute time. It's like having an infinitely patient, super fast programmer on staff.
Wow, debugging its own node.
Yeah.
Okay, so after the engineer runs the test, maybe fixes some bugs, the results then get passed to the analyst, the synthesizer, is that right?
Yes, exactly. The analyst takes all the experimental results, and its job is to figure out what was learned. It synthesizes new insights from that raw empirical data. It looks at the system's own past experiments, including comparing related designs, what they call parent and sibling nodes, to understand the lineage. It's sort of like doing an automatic ablation study, where you systematically take parts out to see what effect they have. The analyst does that virtually to really understand why some designs worked and others failed. And then critically, this learned insight gets fed back into the whole system, helping it evolve and get smarter over time. And of course, it also draws heavily from the cognition base.
Which brings us nicely to that cognition base, the knowledge library, fueling ASI-ARCH. What exactly is in there?
So this is a really carefully curated collection of insights. They extracted knowledge from nearly 100 seminal human research papers, specifically focusing on linear attention mechanisms. Linear attention, just for context, is a type of attention that's much more computationally efficient than the standard quadratic attention you find in many big transformers, especially for handling really long sequences. Faster processing, less memory. So the cognition base is essentially how the system taps into decades of collective human knowledge, distilled into a format the AI can understand and learn from. It gives it a solid starting point for its own innovation.
Okay, that makes sense. But how does ASI-ARCH actually decide if a design is successful? Because we know in AI, success isn't always just hitting the highest score on one benchmark, right? It can be tricky.
You're absolutely right. It's more sophisticated than that. They use a composite fitness function. It's not purely quantitative metrics like, say, training loss or benchmark scores alone, because those can sometimes be gamed by the AI. Crucially, it also includes a qualitative assessment. This is done by a separate large language model acting as an expert evaluator. This LLM judges things like architectural innovation, structural complexity, implementation correctness, and even how well the model converges during training. This qualitative angle is vital. It prevents what's known as reward hacking, where an AI finds a clever loophole to boost a score without actually producing a genuinely good, useful, or novel design. It forces the system to value real design quality alongside raw performance numbers.
Got it. And to handle the sheer number of possibilities it needs to explore to find these novel architectures, they use a smart two-stage exploration then verification strategy. Sounds like balancing speed and rigor.
Exactly that. So the exploration stage is all about speed. ASI-ARCH rapidly identifies potentially promising candidates. It does this by testing them using smaller models, think around 20 million parameters. This lets it sift through a huge number of possibilities relatively quickly. And get this, during this initial phase, ASI-ARCH ran something like 1,773 experiments, which burned through over 10,000 GPU hours. So serious exploration. Then comes the verification stage. Here, the best candidates identified during exploration get put through the ringer. This means scaling them up significantly to 340 million parameters and training them on much larger data sets, up to 15 billion tokens. Really comprehensive validation. This two-stage approach makes sure that the discoveries aren't just flukes on small test cases, but are genuinely robust and scalable architectures.
So you've got this AI system that's constantly learning, adapting.
A craft.
It's even debugging its own code. And it's all guided by this multifaceted idea of success that isn't just one number. It really is this self-improving loop. It lets the AI build its own kind of intuition about what makes a good design, much like a human scientist refines their ideas through trial and error over time. It's an amazing closed feedback loop for discovery.
And if you connect that to the bigger picture, that self-improving cycle is exactly how you break the human bottleneck we talked about. It lets the AI develop its own design principles not just by reading papers, but by actively doing the science experimenting, analyzing, and then feeding those lessons back into its own creative process. This is where you see the jump from just automating optimization to achieving true automated innovation.
Which brings us to the breakthroughs. The paper calls this whole thing an AlphaGo moment for architecture discovery. Now, for anyone who doesn't remember, Google's AlphaGo famously made Move 37 against Lee Sedol, a move that totally baffled human grandmasters. It revealed strategic thinking no human had conceived of. So what did ASI-ARCH actually discover that makes this comfortable? What's the AlphaGo moment here for AI research?
It's a really apt analogy. ASI-ARCH successfully discovered 106 novel, genuinely state-of-the-art linear attention architectures. But what's truly remarkable, the AlphaGo parallel, is that these AI-discovered architectures showed emergent design principles. They systematically outperformed the best human design baselines. So just like AlphaGo's Move 37 revealed these unseen strategic depths in Go, these AI designs are illuminating previously unknown pathways for architectural innovation. For example, maybe it found a completely new way to combine specific gating mechanisms with certain types of convolutions that just wasn't intuitive to human designers, but turned out to be incredibly effective. It's not just quantitatively better, it's qualitatively different. It's fundamentally new thinking.
That is genuinely astounding. So quantitatively speaking, how do they stack up against the human design models? Are we talking tiny improvements or like noticeable jumps?
Oh, these were significant, noticeable jumps.
Wow.
The discovered models consistently outperformed top human-designed baselines. We're talking names like DeltaNet, gated DeltaNet, and even Mamba 2, which itself is a pretty recent and high-performing model. And this was across a range of important tests, language modeling benchmarks, common sense reasoning tests like ARC Challenge, BullQ, HelloSwag, PIQA, Wino Grande, the whole suite. If you look at tables 1 and 2 in the paper, the data clearly shows substantial gains across the board. It's not marginal.
Wow. Just think about that for a second. AI isn't just playing the game better. It's reinventing the rules of how you design the players. It's like a fashion designer who can dream up entirely new styles no human has ever thought of and then instantly creates them and proves they work better. It really feels like a qualitative leap.
It absolutely is. These aren't just tiny incremental tweaks. They reveal genuinely new principles for innovating in attention mechanisms, principles that are distinct from how humans typically think about these problems. It's evidence of this emerging machine creativity that goes way beyond just combining existing pieces in slightly new ways.
And probably one of the biggest takeaways from this paper, maybe the most profound implication, is something they call the new scaling law for scientific discovery. What's that all about?
Yeah, this might be the paper's most impactful contribution long-term. ASI-ARCH established what they claim is the first empirical scaling law for scientific discovery itself. What that means, essentially, is that making architectural breakthroughs, the act of discovery, can now potentially be scaled computationally. This could fundamentally transform AI research progress, shifting it from being human-limited, capped by our brain power and time, to being computation scalable. Before this, you could argue the rate of discovery was tied to the number of brilliant human researchers and how fast they could work. Now, this suggests we might be able to accelerate discovery just by throwing more computing power at the problem.
So what does that actually mean for us, practically? It's just research itself, the process of discovery, can be accelerated just by adding more compute, just like we scale up training for massive LLMs today. The ceiling on how fast we can discover new things just got lifted. Big time. There's a chart in the paper, Figure 1, titled More Computation, More Discoveries. And it just beautifully shows this strong, almost linear relationship. More GPU hours poured in, more state-of-the-art architectures discovered. This isn't just a technical win for AI. Think about the potential blueprint this offers for accelerating discovery in other scientific fields. Imagine drug discovery, material science, maybe even climate modeling, areas where progress has often been bottlenecked by human intuition and the slow pace of experimentation. This paper hints that with enough compute, we might unlock discoveries across the board at a pace we've never seen before.
It absolutely raises that possibility, and it poses the question. If discovery itself scales with computation, what are the ultimate limits to scientific progress? Where does this lead? It provides a concrete data-backed pathway towards, well, towards artificial superintelligence specifically focused on doing AI research. It really could be a game changer.
Now, someone might wonder, okay, these new designs perform better, but is the AI just making them ridiculously big or complex? Is it just brute force?
Hmm.
But the paper looked into that too, didn't it? It's more subtle than that.
Absolutely. They specifically analyzed this and found what they call model complexity stability. There wasn't some trend where the AI just kept making models bigger and bigger to get better results. Most of the successful discovered architectures actually stayed within a pretty reasonable range, around 400 to 600 million parameters. This shows what they term architectural discipline. It wasn't just relying on sheer scale. The AI was finding more efficient and perhaps more elegant designs, not just larger ones.
That's a really important distinction. So the AI is learning to be efficient, elegant even, not just piling on more layers like a human might be tempted to do when stuck. What else did they learn about the AI's design preferences? Did it seem to favor certain types of building blocks?
Well, interestingly, ASI-ARCH did show a preference for some established, well-known components, things like gating mechanisms and convolutions. Now, this likely reflects some inherent biases from the human literature it learned from in its cognition base. Essentially, it learned from what we already knew works pretty well, but here's a key insight. When they looked at the top-performing models, the real breakthroughs in their model gallery, these showed a significantly less pronounced long-tail distribution of components. What that means is the most successful designs didn't rely on a huge variety of obscure or rarely used parts. Instead, they tended to converge on a smaller, core set of techniques that were validated and highly effective. It kind of mirrors how top human scientists and engineers often build on proven, robust technologies to get state-of-the-art results, rather than trying to invent completely brand new, unproven things for every single component.
Right. That shows this sort of emergent intelligence in the design process. It's not just randomly throwing stuff together. The AI is learning what's reliable, what works well, and it's being smart about focusing on those solid, proven building blocks, just like the best human engineers would. It's a really striking parallel.
Exactly. While it's definitely exploring novel combinations and ideas, the designs that really succeed seem grounded in principles that are fundamentally sound and effective, even if the specific way they're put together is new to our intuition. It's this blend of disciplined exploration and consolidation of what works.
Okay, moving to another really fascinating insight. Where did the really good ideas, the breakthrough designs, actually originate from within ASI-ARCH? The paper dug into this, tracking ideas back to one of three sources: cognition, meaning derived from human expert literature; analysis, learning from its own past experiments; or truly original ideas the model generated without a direct prior link.
And here's the kicker. It's detailed nicely in Table 3. While the majority of all ideas generated still came from cognition, basically, learning from human examples, the picture changed significantly when they looked at the top-performing architectures. For their model gallery of breakthroughs, a markedly higher proportion of the crucial design ideas came from analysis insights derived from its own empirical experience, its own trial and error. Specifically, it was something like 44.8% for the state-of-the-art models, compared to only 37.7% for the less successful designs.
And that is incredibly insightful. It really suggests that for an AI to achieve genuine breakthrough innovation, it can't just be a passive learner just reading the textbook, so to speak.
Yeah.
It has to get its virtual hands dirty. It needs to experiment, meticulously analyze its own successes and failures, and really learn from its own experience to push the boundaries. It sounds an awful lot like the human scientific method, actually.
It absolutely mirrors how human science progresses, doesn't it? You can build basic competency on existing knowledge, sure, but true excellence, the kind of work that defines the cutting edge of a field, that often comes from actively engaging in that cycle. Exploration, rigorous testing, summarizing what you learned, and feeding that back into the discovery process, that iterative feedback loop. This finding really underscores the power of the closed-loop system they built. The AI isn't just learning, it's learning how to learn better through experience.
Looking ahead, then, at the real-world impact and what's next, it seems really significant that they're making the complete framework, all those discovered architectures, even the cognitive traces, completely open source.
Right.
They explicitly say this is to democratize AI-driven research.
Yeah.
That puts this incredibly powerful tool out there for potentially everyone to use and build on.
It's a huge contribution back to the community. And the broader implications of AI designing AI, they're profound. They stretch far beyond just making better AI models faster. The paper itself points towards some exciting future directions, too. They talk about things like multi-architecture initialization, basically starting the search process with an even wider variety of initial designs to explore more possibilities. Also, component-wise analysis, where the AI could analyze its own internal framework to figure out which parts of the ASI-ARCH system itself are most crucial for success, like the AI studying its own discovery process. And crucially, they mention engineering optimization for the architectures it discovers, things like creating custom accelerated code kernels to make these AI design models truly efficient and practical for real-world deployment.
So we've seen AI move from just understanding and optimizing to actively inventing, creating this potentially self-accelerating cycle of discovery. We're talking about AI systems that aren't just, out inventing human experts in specific domains like architecture design, but maybe even improving their own design process faster than we can fully grasp. What does that ultimately mean for us, the human researchers? What's our role when our AI partners become these autonomous engines of innovation?
That really is the profound question hanging in the air, isn't it? If AI can autonomously conduct the entire scientific research process, from dreaming up novel hypotheses all the way to rigorous empirical validation, how does that change our own understanding of creativity, of intelligence itself? What new frontiers suddenly become possible, not just in AI, but in all of science and technology, when the very tools we use for discovery are themselves self-improving, pushing boundaries in ways we might not have even conceived of? It certainly challenges us to rethink the future of invention.